Okay, hello everyone. My name is Kelly Dudley and I'm with the New Center. I'd like to welcome you to today's webinar titled Overcoming Barriers to Adoption of More Sustainable Concretes. And we're so glad you could join us. Video recording in PDF of the presentation you're about to see will be uploaded to the new website, newconcrete.org, following today's webinar. Now, attendees are in listen-only mode, and because we're recording the webinar, we will be taking questions via email at info@newconcrete.org. The ideas expressed in the following presentation are those of the speaker and do not necessarily reflect the view of the New Center, ACI, or its committees. As with all concrete mixtures, trial batches should be performed to verify concrete properties. Results may vary due to a variety of circumstances, including temperature and mixture components, among other things. You should consult your materials, cement, and concrete professionals for assistance regarding concrete production or placement. Nothing contained herein shall be considered or construed as warranty or guarantee, either expressed or implied, including any warranty of fitness for a particular purpose. Today's speaker is Professor Doug Hooton. He is the NSERC CAC Industrial Research Chair in Concrete Durability and Sustainability. His research involves finding ways to reduce the greenhouse gas emissions associated with concrete infrastructure. He investigates the use of materials such as supplementary cementitious materials, ground limestone, to produce a stronger and more durable concrete product. His research has informed the specification codes associated with the American Concrete Institute, the Canadian Standards Association, and ASTM standards. He has conducted research on slag cement since 1975. And now I'll hand the presentation off to you, Doug, to get started. So thank you so much.
Thank you very much, Kelly. And good afternoon, everyone. I assume it might be afternoon where you are, unless you're on the West Coast, I guess. So I'm going to talk about an outline, and people like to talk about sustainability, gives them stomach upset. So I brought Pepto-Bismol with me. So I'm going to start with where we are now, some of the industry sustainability objectives, and then dealing with some of the, recognizing there are barriers to change. People generally don't like change because they're used to doing what they've always been doing. And then developing action plans to try and overcome some of those barriers. But I thought I'd start and just talk about this. People talk about concrete being high carbon emitter. But concrete is sustainable. It has the lowest embodied carbon and energy footprint of any construction material, at least on a mass basis. And it mainly uses local materials and typically has a long service life and is recyclable at the end of its service life. But we still need to do things better to reduce the global warming potential. So this is some data from the University of Bath that was developed some time ago, but it shows embodied energy on the vertical axis, embodied carbon on the vertical axis, embodied energy on the x-axis. And you see all the materials lined up there. And concrete is on the lower left, which means it's the lowest on a mass basis per kilogram of any of the building materials. And if you look at cement, which is the biggest contributor to the global warming potential in concrete, is further up, and also that blue box, the blue circle there. Now, the other materials, let's see, glass, steel, even timber are up further on this. And again, a lot of this depends on how you account for things, but they were looking at all building materials and not with any reference to any one. So what causes this is that we use over 20, in fact, this is probably out of date, billion tons of concrete each year. So the global impact of concrete is about 7% of the anthropogenic CO2 that's emitted and almost 4% of the energy. However, in the industrial nations like Europe and US and Canada, it's only in the range of 1% of total emissions. And that's EPA data. But the big players in this market, or the large volumes here, the 20 billion tons, they're coming from China, India, and it's growing in Africa. China produces more cement in 2 or 3 years than US did in 100 years. So it's a different scale. But again, Portland cement is just one part of the concrete. It's concrete. If you look at this this is concrete data About 96% of the CO2 coming from concrete is coming from the cement, the dark blue. And about 85% of the embodied energy is also from the cement, if you're only using Portland cement concrete. And most of the global warming potential in concrete is based on its embodied CO2. We don't have a lot of the other types of issues. However, the US concrete industry has reduced its carbon footprint significantly since between 2014 to 21. And that's based on industry-wide third-party EPDs, environmental product declarations, surveying all their members on 3 different time periods, 2014, 2019, 2021. And you can see they've reduced their carbon footprint by 21% over those 7 years. And that was before Portland limestone cements were introduced really in a big way in 2022. So it doesn't include that part of it. And it'll continue to go down. So the reduction between 14 and 21 is largely thought to be due to the increased use of supplementary cementitious materials. Now, the whole industry, the cement industry, is focused on accelerating its reductions in global warming potential. And they have developed a roadmap, came out in 2021. The Canadian Cement Association just came out with one recently. The Europeans have one as well. And they follow a similar approach. They want significant reductions by 2030, in embodied CO2, and net carbon neutrality by 2050, which is the sort of global goal. However, to get to net carbon neutrality is probably going to require things beyond what I'm going to talk about today, including carbon capture and sequestration and use of non-CO2 emitting fuels like hydrogen or electric firing of kilns. And of course, so I'm going to go back to that one. And of course, there's 5 points to that on the chain in the bottom. They start with the cement clinker, which is where most of the CO2 is coming from. And then how much clinker goes into the cement that's sold. And then cement is how you minimizing the cementitious materials in concrete. And of course, there's things you can do in construction to reduce the amount of concrete that's used, more efficient designs. At the very end of life, or during its life, concrete also carbonates to some extent. So there's some CO2, approximately about 8% of its initial CO2 is taken up by the concrete in the structures over its service life. So what are the low-hanging fruit? If we're going to go for 2030 goals, which is only, 7 years away, we've got to do things now. And so the things we can do now, the low-hanging fruit that's available in the market now, and they're allowed in standards, including the building code, use Portland limestone cement. They offer about a 10% CO2 reduction over straight Portland cement with very little change in performance. I shouldn't say no change in performance. There might be small differences in admixture dosages required, and you have to do optimization, of course, with any new material. Increase the levels of supplementary cementitious materials in the concrete. The proportion of CO2 reduction is proportional to the cement replacement. You're replacing cement clinker by putting SCMs in the mix, as long as you're not increasing the total cementitious materials content. And one that only gets mixed results, but I mean, it has great results, but it's not being used very effectively in North America, is optimizing total aggregate gradations. You can reduce the cement paste fraction by better packing of the aggregates, which typically need at least 3 size ranges of aggregates to combine together to optimize. And you can significantly reduce the amount of cement paste you need in the mix by about 5 to 15%. At the same time, you get reduced shrinkage, reduced concrete permeability, because the shrinkage and permeability are taking place in the paste fraction. So if you reduce the paste fraction, you're going to reduce that. And of course, chemical admixtures allow us to do that while maintaining the required workability for placement. But even when we're trying to deal with these low-hanging fruits, there will still be barriers that need to be addressed along the construction value chain. When a change in concrete comes along, the new materials always get blamed for any problem that occurs in concrete. And problems occur every day of the week in various applications. One example is this slow adoption of 1L cements, which is under C595. They were approved in 2012 in the United States through ASTM and AASHTO, even earlier in Canada. And they meet all the same setting time and strength development requirements as a type 1-2 Portland cement, but have lower CO2 emissions by 10%. They've been used in Europe for almost 40 years now. And they have been used in some US states for almost 20 years now. Colorado and Utah are 2 examples, and they were used before 1L was available under the 1157 performance specification. So it's been used in interstate pavements and other applications since 2005. Therefore, transitioning to 1L cement should have been relatively simple, but it hasn't been the case everywhere. And why did the cement plants suddenly stop producing one in some areas and jumping to 1L? Because of supply chain restraints. Cement plants and terminals don't have the silo capacity for holding a cement that's not being purchased by their customers. So if they weren't required to use 1L, nobody would order 1L. If you make it 1L, then they don't have room for 1 and 1L in their silos, especially when there's a shortage of cement materials. So this forced them to jump into an adoption of 1L cement. So in 2022, it was adopted. They made decisions in certain regions to jump right into it. And so last year, the 1L grew to about 25% of the total US market. It's much higher in Canada. Most, also on the supply chain issue, most concrete plants don't have the extra silos for handling additional cements. So if a concrete producer wants to use 1L cement, they probably don't have room to have 1 and 1L in the same plant and have whatever their favorite supplementary material is, fly ash, slag, or whatever it is they're using. And all DOTs pretty much accept 1L cement. So that's not the DOTs that are holding us back. Now, not everybody's a fast adopter. There's some reluctance to specify. Like I say, 2012 is when they were adopted in the standards. Some DOTs took longer than others. Caltrans, for example, was a pretty slow adopter. It wasn't until 2021, I believe, or November 2020, where they had finally adopted it. Sorry, it was 21. And only after they did their own internal study showing it did no harm and offered. And it turns out the study that was shown in that was done for them showed exactly the same things that had been shown earlier when it was developed. But there's a lack of trust in the industry in some of this reluctance to move on to new things, and lack of trust in the experience and research done by others. It wasn't done in your own backyard sort of thing. So just take 1L cements into the specifications, then we're not going to make this deadline. We don't have 9 years left to meet 2030 targets. So we need to accelerate the adoption. And there has been pushback. In most places where type 1L was rolled out, there's very little concern. People are just using it. If there was no change, they made minor adjustments. It's typically what you do anytime you switch cement supply at a ready mix plant. You're going to do your own in-house verification of your water content, your admixture requirements to get the materials you need, or to get the properties you need out of your concrete. But in some areas where it was introduced, it was as if the sky had fallen. And this seems carrying on in certain areas, but it's not huge areas. So rule number one, going back to what I said earlier, the new material always gets blamed for any problem. So when people have problems, if there was something new in the mix, that's what gets blamed. It's not the first time that's happened in my career. And so these are some of the examples of claims. People claim all kinds of interesting things. Strength losses at 28 days since switching to 1L, 1,000 PSI loss in a 5,000 mix, more fluctuation with air contents. Again, that's admixture adjustments. Having to increase PLC by at least the amount they took of the limestone in the mix, negating any effect, lower setting times, increased shrinkage and cracking. One contractor claimed a 50% loss in strength, and you know that's not going to be accurate at all. So people are blaming anything that happened to them on this new adoption. And you start asking questions, and I've talked to various ready mix producers in various states where they've had some issues. It's typically you find out other things were happening at the same time, or there's other causes. But again, new material always gets blamed, and negative news travels fast and often gets exaggerated as it gets passed along. It's like bad news everywhere with the internet. But there's lessons to be learned by everybody involved, including the cement industry. You only get one chance to make a good first impression. When introducing any change, the industry has to supply sufficient customer support and communication to help that transition, especially with the smaller independent producers. A lot of the big integrated producers were aware of it, so they didn't have any issues. And again, helping make changes to what the required changes, giving suggestions on admixture changes and other minor adjustments. But we need to anticipate these and overcome these barriers to meet targets. The transition should have been an easy change to more sustainable concrete. But it's taken 11 years so far and it's not yet complete. They said about 25% last year in the US was put on cement. If we can't make that simple change by 2030, then how are we going to meet targets with other changes that are likely coming? They're going to have bigger impacts. So we need to better understand these concerns and address the barriers along the construction value chain to help speed things up. So where are the barriers? People think standards and specifications and codes are the barriers. They're often seen that way. But many of the levers that I'm talking about for improved sustainability are already allowed in codes and standards, but they're not always widely accepted in practice, either due to perceived risk or supply chain issues. These include the Portland limestone cement, sufficient levels of supplementary cementitious materials or blended cements if they're available in the market, and optimization of total aggregate gradations to reduce the amount of paste in the concrete. And you think that would be in the ready-mix concrete producers' best interest if they have the bins for it, because cement's the most expensive component of their concrete. And specifications are changing. We now allow ground glass pozzolans, 1866 standard. 618 has been changed this year to allow landfill coal ash to be harvested because of the reduction in the amount of coal power plants still producing with quality ash. A lot of the stuff that's in landfills is better quality than the currently produced ash at a number of these plants. And it's being it now is allowed to be processed to meet the requirements and sold as fly ash or as coal ash. We're looking at a new performance spec for supplementary cementitious materials. That's still being validated. And the ASTM 1157 performance specification for hydraulic cement has existed since 1992, so over 30 years, but it's rarely specified. Because apparently everybody talks about moving to performance. We wish they had a performance standard that wasn't prescriptive, but when you give them a performance standard, apparently they don't trust performance. So very few people have adopted that, very few states or other specifiers. And that's too bad because it's just, they seem to want to know what the ingredients in the cement is, as opposed to trusting the performance. It's like saying, well, I wonder what metal's in the car body of my car, as opposed to saying, I want it to last 10 years without rusting. Again, we need more standards that are less prescriptive, but there's also non-hydraulic cement materials being developed. There's sort of the more radical out there versions of different materials that are potentially coming on the market. We don't have one for geopolymers that's set, or for cements that's set by carbonation in terms of standards, although we're getting close with the carbonation cement standard. And of course, having a national spec means before you can go into a building code like the ACI 318, you've got to have a national specification. And some of these new materials, that radical ones, and I'm not talking about the low-hanging fruit here, I'm talking about these new sort of further out there products. The test methods we have in C94, for example, some of them, the new materials can't be tested standards without making some small adjustments because they perform differently. Now, ACI 318 does permit the use of alternative cements as long as the LDP, the licensed design professional, approves it and the code official on that who has jurisdiction on that project allows it. And the International Code Council has an evaluation service that has developed AC 529, an acceptance criteria for low carbon alternative cements. So it's an evaluation process, but I'm not aware that anybody's actually used it yet. And of course, one of the problems with specifications is specifiers aren't always using the latest specifications, the latest ASTM specs, the latest building code version. They often design firms cut and paste from previous projects because it's seen that we've done it before, it's easier, there's low risk. Some specifying authorities they want performance, but they add prescriptive limits on materials and mix designs. Prescriptive minimum cement contents are not helpful if we're trying to reduce carbon emissions. And a lot of these minimum cement contents were based on work that was done 50, 60 years ago, before chemical admixtures and SCMs were on the market. And some of them don't allow to use supplementary cementitious materials or to optimize for their use. Again, because of old prescriptive specifications that have been there for decades. And unfortunately, when you start adding prescriptive requirements on top of performance, it confuses the roles and responsibilities of people the contractor, the specifier, the producer. And it leads to concrete that may not meet the expected performance and results in less sustainable concrete in the end. So current prescriptive requirements can make it difficult to adopt materials in mixed proportions that can lower global warming potential. For example, 318, just as one example, only required for chloride exposure, a C2 exposure, they only say to meet that, you have to meet strength limit, 5,000 PSI, or a maximum water binder ratio of 0.40. And apparently that gives you corrosion resistant concrete for structures, but that's not, those are indirect measures. Strength is there as an indirect measure of the water cement ratio, and water cement ratio is one input into what makes low permeability concrete that will resist chloride ingress. But they're not testing any direct measure of that chloride resistance. So they don't, and there's only one variable here. C2 covers all chloride exposures in 318. Typically, we don't need 5,000 PSI, you need low permeability, but we're not measuring anything that tells you that in that code. And just as an example, this is some work that Michael Thomas did, shows here's the Coulomb charge in the vertical axis versus water cement ratio on the x-axis. And it shows three different concrete: straight Portland cement, 25% fly ash, and a 25% slag plus about 5% silica fume. And it shows at the same 0.40, you could have a 2,500 Coulomb concrete with the Portland, about a 1,500 Coulomb concrete with the fly ash, and less than 1,000 with the green mix there at the bottom. So they'd all meet the C1 spec if there were 5,000 PSI and meet the water binder ratio, or the C2 spec, sorry, in 318. But they're all completely different durabilities in terms of how long those things are going to last chloride exposure. So we're talking about decades of different performance based on the different penetration resistance of those concretes, but they're all equal under the code at present, because there's no performance measure. So that's something we're trying to address, but it's an uphill battle. So let's talk about the risk to adoption of new technologies. I mean, life safety, of course, is a big risk, and certainly we're not going to compromise on that. It's the primary focus of a building code. And one of the issues with some of the really novel materials is they haven't been tested for structural properties. Therefore, everything isn't there that's needed. Bond strength, flexural strength, shear strength, fire resistance, all those things that would be needed for a building code. But the economic risk is the bigger risk, because the materials I'm talking about aren't the life safety issues. They're known materials, just in different proportions. So it's more nuanced, the risk here. So people see different risks, both the producers and contractors, and those that are ultimately the owners of the structure. So where do people see risk? Suppliers and contractors see economic risk when changes that occur that affect their profitability or negatively impact productivity or the ability to achieve full payment for their work. So there may need to be incentives in contracts to incentivize meeting global reduction potential, global warming potential targets. Owners experience risk from loss of functionality, increased maintenance, or reduced service life if a poor performance occurs as a result of using these new materials. And so adoption of new technology requires some sharing of risk. Non-equitable distribution of perceived risk can result in over-design and derail the implementation of a new technology or get rid of any global warming benefit that occurs. So to move forward, everybody needs to be involved in that process. Not knowing why changes are being made ultimately leads to resistance. Engineers, designers, contractors, and trades all need specific technical training to implement these strategies or to be aware of them and how does it affect them. The licensed design professionals need to implement new technologies in ways that allow tradespeople to perform the construction. Shouldn't make it more difficult for them. Tech transfer and skills trading are imperative for success and to avoid failure, because nothing sets back innovation faster than a single failure. Now, a lot of the professional design professionals who are in positions of authority are not materials experts. Concrete's that gray stuff that goes between the rebars they design. Nor are they always focused on methods for adoption of sustainable technologies. So we need educational programs to make professionals aware of these options and to inform them on the benefits and potential concerns they need to deal with when different sustainable technologies. Some of them are no-brainers, some are more difficult. So they need it, and this also needs to include any impact on scheduling, which will affect the costs. Jumped. We need to provide the designers with practical tools for specifying sustainability targets, for assessing responsive bids, and as monitoring construction. We need more tech support to reduce the risk for early adopters, and that's where some of the incentives come in. No one wants to be first. Once something is adopted and it's successful, then that risk seems to go away with most technologies. This is just an example that when you're looking at different global warming reductions, there are some different issues here. This was an example from courtesy of Bill McLaughlin at Elliston. They're looking at a project in Western Canada where they asked the producers, they had 3 different producers that cost concretes that had different global warming potentials for projects. So they each had a baseline concrete and then they had low carbon packages. And the one here, I circled the one on the left, company number 1 had the lowest cost and a big reduction in CO2 on the right. Company 2 put a couple of packages in, their cost was a bit higher, and when they went to another package, it would have affected their scheduling on vertical construction by an extra 1 to 2 days per floor or per pour on vertical construction. So that's a huge impact on scheduling. Company 3 had the lowest carbon global warming potential without affecting the construction schedules with that package number 1 that I've circled. And they had another one that was even lower, but it would have again affected the construction schedule. So the optimum in terms of lowest global warming potential was without affecting schedule was that one on the right. Okay. So what do we need to do to help the contractors and trades? Contractors need sufficient information to successfully bid on and compete on a project that has sustainability requirements. They're used to dealing with quantities of concrete, the types of concrete, and getting prices and all that, and when they're doing a bid. They need to understand how to bid with sustainable mixers. And then, in other words, they need to know how it's going to affect their schedules and what's the change in what's the green premium like the cost of doing so. And they need to inform their subcontractors hesitant with trying new products. Impacts of new technologies may be small, but they typically require changes to traditional practices. Might be just difference in the way it feels to the finishers, or the timing of the finishing. But it's just like when self-consolidating concrete was introduced, every contractor experienced a formwork blowout because they weren't used to they could place the concrete in these high lifts very quickly, but the formwork wasn't designed for it. But they know how to do that now. When silica fume was introduced in the 1980s, the lack of bleed water resulted in finishing and plastic shrinkage problems. But that could be alleviated with fog misting or use of evaporation retarders on the surfaces to prevent that from happening. Now, some people still have an aversion to silica fume because they're still remembering the 1980s. So high SEM levels may affect finishing times as well, especially in cooler weather. And they also may require longer curing to reach the performance you need. So that needs to be called out in the contract. If you're going to do sustainable mixes, that will affect scheduling. And so we need workforce education. There's an immediate need to work with our associations like ACI, organizations, the cement industries, or other trades organizations, product organizations that serve tradespeople and professionals working in the industry to provide training on these strategies, to just explain them. So it's not just mysterious. It's not like there's some different concrete on here today. Let's make the best of it. And so ACI could just have a role in this, and maybe the new will take on some role. We need training sessions for individual work in key companies to make them the key people within their companies who can transfer that knowledge within their organization. And some of that will come at a cost, but that needs to be included in the cost of implementing the technologies. And people who want low carbon concrete need to recognize that there's the green premium isn't just the materials, it's part of all that dealing with the risk that everybody's feeling when they're bidding on projects and the need for education. So there's a lot of activity in the policy end of things. Various state agencies and other groups, NGOs are involved with policies to create a higher demand for low carbon. But some of these policies are being made in a technical vacuum. And some of these policymakers don't have sufficient knowledge of the industry supply chain and infrastructure. There are many types of concrete used on the projects, for example, so you can't just say we're going to set an emissions target for concrete, because one project will use multiple types of concrete. So you need to carve a global warming potential budget for that project, not on the specific mixtures, to allow that constructability, because a mass foundation, you can wait on that. But vertical columns, you can't wait on that because that's going to affect schedule. So you need different mixes used, and they'll have different global warming potentials in those mixes. But you want to do it so it allows the flexibility of the builder to get it done in a timely fashion. And so people need to understand the complexity of the problem, and that's some of the work I've been doing with my colleagues with Breakthrough Energy and now with ClimateWorks to try and talk about some of these issues, get people involved so they're all understand what's going on. So you can't make a change for one segment of the market. And we got to recognize that the level of technical knowledge through the supply chain varies. Not everybody's on top of their game or fully educated on all the issues. So there's a need to provide technical information to educate policymakers as well, so that laws and regulations are developed are practical and implementable. Passing rules and legislation that can't technically be achieved only serves to build resistance in the user community and hinders progress. And so, as I mentioned before, the green premium for low carbon concrete is not just the materials cost, it's costs associated with CapEx for material suppliers, increased contractor bids due to perceived risk, at least at the beginning, contractor workforce training, and any additional quality control, quality assurance testing needs to monitor performance when implementing a new kind of concrete for the first time. People want to know more about it and see that it's working. It may require more testing. And now one thing, just as I'm talking about these more radical low carbon materials, not the things we can do now, but as people come up, we hear about new products every day coming out. But what they need to realize is that there's an existing infrastructure in the concrete industry. So if you're going to have some new material, it has to be able to be batched into a ready mix plant, batched out of a ready mix plant, and delivered in trucks and taken to a job site. It has to meet the existing infrastructure that's available. And that often, because making changes to that infrastructure is hugely capital intensive. And so we've got these low carbon, people developing low carbon products need to think about that as well. So to address the risk, one of the things that we've been dealing with is trying to develop demonstration projects. The biggest barrier is the perceived risk. So no one wants to be a first adopter. So if we do demo projects where these materials can be put into practice under real world conditions, where there's some underwriting by a third party or the owner, which in some cases might be DOTs, or maybe the GSA or the IRA, with some of the IRA funds coming out. You can try out products and make sure they work in the field. They can be successfully mixed, transported, and placed. And those projects need to be ones that pose no risk of life safety in case there's something doesn't work. City of Portland's done some demo projects for low carbon concretes, and they have a carbon budget approach, the way they approach projects as well. And they're not alone, that's just one example. So demo projects help deal with this collaboration between the material suppliers, contractors, and owners. There's a risk sharing. There's technical assistance provided before, during, and after construction, and performance is monitored. And we need a broad dissemination of results to build confidence in the industry. So if there's a good experience, we need to talk about it, make other people aware how it was done successfully. And in 2022, the Min Road project was done just south of Minneapolis, and with a whole series of experimental concretes that Larry Sutter and Tom Van Dam were actively involved with the DOT there in doing so. And they demonstrated several products that worked well. Some of them didn't work well. The base mix in this case, they had to work downhill from on a global warming potential, had a 1L cement and 20% fly ash. The ones that had success, the notable successes, ones that went further, were a type L with 20% limestone with the fly ash, and a 1P 30% calcined clay mixture of cement. It's just a sketch of that Min Road project. They have a section of I-94 where they can divert traffic onto the test section, or if they're looking at the test section, they can put it back onto the main lines. Runs for several miles there. So it allows them to test the performance in the field and allows them to place it. So they placed it in ready-mix trucks with concrete pavers and did all that in real time. So for new demo projects, where are the big plays? Well, 70 to 75% of the Portland cement and blended cement in the United States is used in ready-mix concrete. About 15% in precast concrete. And of that 75%, about 54% is used in the construction sector, and about 43% of that towards the public works sector. The four largest single uses are residential buildings, almost 40%, streets and highways, about 30%. Those are the big plays. So they have high volumes of cement use, therefore similar opportunities for carbon reduction. But if you're going to worry about the building codes, then the infrastructure probably has less concern with life safety than, say, a building. In terms of using building codes, they're focused on life safety. So the infrastructure may be the easiest approach. Public sector changes need to be approached on a push-pull basis from the technology engineering side and the policy legislation side. And so public works projects are the lowest common denominator in getting some of these producers working with the DOTs. So in summary, well, Portland cement-based concretes will still be used for most concrete applications. To meet 2030 global warming potential reduction targets, concrete's carbon footprint can be significantly reduced by adopting the materials and tools we have today. But we need to accelerate their adoption. And one way to do that is the demo projects. And we need to address the perceived risk along the construction value chain. Everybody has to be involved in the conversation. And where required, we need education of those people, to just education in terms of how does this affect my job? Because everybody's risk adverse. If they don't know what's going on and something's changing and they're not comfortable with it, they're going to have risk. They're going to be risk adverse. But if you can explain to them what potentially might happen, then maybe that some of that risk goes away. And real world demo projects will show where these can be placed with current construction infrastructure. So thank you for that. And I'd be happy to answer questions if there's any. And the next talk will be on June 29th. By Tom Tietz from California Nevada Cement Association on some of the legislation issues going on in Bill 9596 in California.
Thank you so much, Doug. I appreciate it. Okay, as mentioned, our next webinar for new is on June 29th of this year at 10 a.m. Tom Tietz will give a very informative webinar, so please feel free to join us. That concludes the webinar for today. Please visit the new website at newconcrete.org for more information on this topic. While you're there, please check out our resources on lower carbon concrete production and placement. And our website provides access to our sustainable concrete guides, frequently asked questions, webinar recordings, and more. And again, we're happy to answer any questions you may have further on this webinar at info@newconcrete.org. Thank you again for attending today's webinar.
Thank you, everyone.